Welcome to Chapter 2. In Chapter 1, we argued that quantum computing rests on interference rather than on brute force parallelism. Now we build the mathematical objects themselves. We introduce the qubit and its state vector, the amplitudes that describe it, the block sphere picture shown in the center, and the Born rule that connects the description to what an experiment actually records. Then we combine qubits with the tensor product and meet entanglement, the correlation that has no classical counterpart. Every claim in this chapter is backed by a short NumPy program you can run yourself. A classical bit takes one of two values, 0 or 1. A qubit is the quantum version of that object, any physical system with two distinguishable states that we can prepare, manipulate, and measure. As shown on the left, the spin of an electron, the polarization of a photon, and two energy levels of a superconducting circuit all serve equally well. What matters is the mathematics, not the hardware. We label the two states using ket notation, which is simply a compact way of writing a column vector. Ket 0 is the column 1, 0. Ket 1 is the column 0, 1. Together they form the computational basis. The essential departure from classical bits is that a qubit may occupy any superposition of the two basis states, alpha times ket 0 plus beta times ket 1. Alpha and beta are complex numbers called probability amplitudes. They are not probabilities. Probabilities are non-negative real numbers, while amplitudes carry a sign and a phase, and that is precisely what allows them to cancel. Normalization requires that the absolute value of alpha squared plus the absolute value of beta squared equals 1. Two superpositions get their own names, plus and minus. Both are equal mixtures, differing only in the relative phase, the minus sign in front of ket 1. Multiplying an entire state by a phase factor leaves every measurement probability unchanged, so a global phase carries no information and only relative phases matter. Together with normalization, that reduces 4 real numbers to 2. Every qubit state can then be written with a polar angle theta and an azimuthal angle phi, which are exactly the spherical coordinates of a point on a unit sphere, the block sphere. The north pole is ket 0, the south pole is ket 1, and the equator carries the plus and minus states. Note the half angle, and one warning, this picture works for a single qubit only. Measurement is the bridge from the description to what an experiment records. The Born rule says that measuring alpha times ket 0 plus beta times ket 1 in the computational basis gives outcome 0 with probability the absolute value of alpha squared, and outcome 1 with probability the absolute value of beta squared. Max Born proposed this in 1926, and it is a postulate, not a theorem. 3 consequences, listed on the right. The outcome is genuinely random even with complete knowledge of the amplitudes. The state collapses, so the superposition is gone, and you cannot learn the amplitudes from a single copy. Here is the whole idea of simulating a qubit. The state vector is just an array of complex numbers. We build ket 0 and ket 1 as two-element arrays, then form a state with theta equal to pi over 3 and phi equal to pi over 4. The inner product of the state with itself confirms that the norm squared is 1. The Born rule then gives probability of 0 equal to 0.75 and probability of 1 equal to 0.25. Sampling 10,000 measurements with a fixed seed returns frequencies 0.7558 and 0.2442. A single qubit is not yet a computer. To combine qubits, we use the tensor product. If qubit A is in one state and qubit B is in another, the joint state of the pair is their tensor product, and for basis states, we abbreviate ket 0 tensor ket 1 as ket 0, 1. Two qubits therefore have 4 basis states, with 4 amplitudes whose squared magnitudes sum to 1. In general, n qubits require 2 to the power n complex amplitudes, which is exactly the exponential growth we met in Chapter 1. In NumPy, this tensor product is the Kronecker product, np.cron. Now the question that separates quantum from classical information. Can every 2-qubit state be written as a product of 2 single-qubit states? The answer is no, and the states that cannot are called entangled. The 4 Bell states, named after John Stuart Bell, are the standard maximally entangled pairs. Take phi plus, the equal combination of 0, 0, and 1, 1. Measuring both qubits gives 0, 0 half the time and 1, 1 half the time, and never 0, 1, or 1, 0. Yet each qubit examined on its own behaves like a fair coin. The correlation lives in the pair, not in either member. 2 prohibitions shape everything. First, entanglement does not send signals. If you hold half of a Bell pair, your own statistics are those of a fair coin no matter what your partner does, and the correlation appears only when the 2 records are compared over an ordinary classical channel. Second, the no-cloning theorem, from Wouters and Jerk and independently Deeks in 1982. No physical process copies an arbitrary unknown state. Unitarity forces the inner product to equal its own square, so only orthogonal or identical states can be copied. That is why copy and vote error correction is unavailable. Let's recap. A qubit is any 2-level quantum system, described by a state vector whose complex amplitudes satisfy normalization. The absolute value of alpha squared plus the absolute value of beta squared equals 1. Because a global phase is unobservable, every qubit state is a point on the Bloch sphere. The Born rule turns amplitudes into probabilities, the outcome is random, and measurement collapses the state. Qubits combine through the tensor product, giving 2 to the power n amplitudes. States that do not factor are entangled, and no cloning follows in 3 lines from unitarity. Next, quantum gates and circuits.